All right, welcome to worksheet number 19, area and distance. We'll talk about different ways to calculate area and distance of certain things. We know how to calculate the area of a rectangle. We know that length times width. We used that before. And a circle, area is pi r squared. So those are nice shape, and we know the formula to calculate the area. How about the shapes that don't have these area formulas? So like if I have a random shape, like how do you calculate the area of that? In this section, we'll learn how to approximate the area, and then from the approximation we'll talk about how to get the exact answer by using the concept of limit. So let's look at the first example here. Example 1, estimate the area under the curve y is equal to x squared. If I wanted to sketch the graph of x squared, I'll start from 0, 0, and then, or it goes here, but I'm going from 0 to 1. So from 0, 1, when x is 1, if you plug in 1 here, 1 squared is 1, so I'm going to end it up there. When x is 0.5, if you plug in 0.5 here, 0.5 squared will give you 0.25, so it's going to go through this point. So I'm going to approximately graph like this, right? So basically it says estimate the area under the curve. So I'm looking for this area here, right? So this is not a rectangle, this is not a circle. It's some random, it's not exactly triangle, right? So this is some random shape that's formed by x squared, right? So I'm going to try to find this area. So the question is, how do I do that? So our first strategy is we're going to try to estimate. So for this function, we'll need to estimate the area. I don't know how to get an exact one yet. Estimate. So this is our strategy. We'll subdivide the interval 0, 1 into 4 equal subdivisions. Okay, so yeah, okay, so then we'll do here, 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 here. So we have 1 interval, 2 interval, 3 interval, 4 intervals. So I'll divide into 4 subdivisions, right? And what we're going to do is, this is what we're going to do. If sum of the area of the rectangles, so you notice that this symbol R4. So this is what I'm going to do. I'm going to create rectangles, right? Because rectangles, I know how to find the value of. So I mean the area of. So at 0.25, my function is right here. So I'll use that as a height of a rectangle. So it's like this. And then for the next interval, I'm looking at the right endpoint. So here you notice the letter R, it just means right endpoint. This is here, I'm going to look for right endpoint of each interval. So the second subdivision, I'm looking at the right endpoint, 0.5. My graph is right here. So I'll use that as height of a rectangle. So I'll use this red rectangle here. And then for next sub-interval, I'm going to kind of do the same thing. So 0.75, that's what I'm going to do here. And the last one is 1, so it's a tall one. Maybe move it down a little bit. Tall graph right here. So what I'm going to do is I'm going to calculate this rectangle, area of this rectangle, this rectangle, this rectangle, this rectangle. It's not going to be exactly the area I was looking for under the blue line, but that's going to be my estimate. So how do I calculate the area of each rectangle? That's not too bad. The length is 0.25 for the first one. Height, how do I know the height? Well, it's 0.25. The blue graph is x squared. So how do I find the height? Plug in 0.25 into x squared. So 0.25 squared, that'll be the height, right? That's gonna give you the area of the first rectangle. If I calculate 0.25 squared, I get 0.0625, 0.0625. So here, let me zoom out a little bit. So it'll be 1/4, which is the length, 0.25 is the length of the first rectangle. Height is 0.625. So I'm going to write 0.0625 plus 1/4 times. Now I'm going to look at the second rectangle. Again, the length of the rectangle is 1/4, that's the same. And the height is going to be 0.5 squared because it's y squared is the function. So 0.25. So I'll use that. And so on and so forth, 1/4 times. The third one is 0.75 squared. So that will be, if you calculate that out, you're going to get 0.562. So 0.562 plus 1/4 times the last one. 1 square is just 1. That's nice, right? So basically, I'm just going to calculate that out. Maybe there's a little bit of shortcut. I noticed there's a 1/4, 1/4, 1/4, 1/4. So I'm going to just factor that out. 0.0625 plus 0.25 plus 0.562 plus 1. And once you calculate that out, my final answer will be 0.468625. Okay, so this corresponds, maybe I should use a red one just because I used the. So this corresponds to the total area of this red boxes, rectangles together combined. So this is overestimate of the area that I was looking for, the blue one. Clearly, this red boxes, the red rectangles are more than the area I was looking for originally. All right, let's look at the next one. So do we always have to use the right endpoint? The answer is no. We can use the left endpoint here, L4. So each interval, first I use the right endpoint to determine the height, but I can use also left endpoint to determine the height. Here, to illustrate, so the first one, left endpoint is 0, so there's like no height. So I'm gonna use green. So I'm gonna just draw the line. So there's like a box with no height. And then for the second interval, where is my left endpoint is here, so I'm going to use that as height. So I'm going to get this box for the second one. And the third one is going to be this box. And then the fourth one is going to be this box, right? So with the left hand, so I'm going to put like highlight like this. So how do I actually calculate the area of these? The first one is going to be 0. So 1/4 times 0 plus second one is 1/4 times second one corresponds to this height. We already know the height, 0.0625. 0.0625 plus 1/4. The third box, the height is 0.025. 0.025. And then the last box is this one. Height is here. We already knew that, 0.564. Again, I'm going to factor out 1/4. And then kind of do the calculation, 0.0625 plus 0.564. And when you calculate that out, I get 0.21125. I know it's tedious calculation, right? So this is my right R4. 4 means I'm using 4 sub-intervals. I'm using right endpoint as a height. That's for the red one. So maybe I should circle it as red here. And then L4 is, I'm using, again, 4 means I'm using 4 intervals. And then I'm using left endpoint as height. So I get that and I get this. So from here, what can I say is, then I can say the actual area A is somewhere between 0.468, oops, the other way around. Let me erase that part here. 0.46825 and then bigger than 0.211251, right? So that's my estimate. It's somewhere between this number and this number, right? All right, so that's our estimate. The next question is how do we make a better approximation? So here we happen to use 4. So do we always have to use 4? Can we use like 100 or can we use 10 or can you use 1,000? The answer is yes, theoretically we can. You just have to use more subdivisions. So I'll use more subdivisions. So let's look at the next case. Let's say you have a continuous function. So that means I'm just going to make more rectangles. So that'll give you more accurate approximation, right? So instead of using 4, maybe I'll use 8, then I get slightly better approximation. So let's look at that here. So let's say you have a function, so some random function goes from A to B. So it doesn't have to go from 0 to 1. It can go from any number to any number. And I'm interested in finding this area S here. So we'll subdivide it into n equal subdivisions. So n could be 5, it could be 10, it could be 100, whatever, right? So I'll just ... So we'll just subdivide into a bunch of different places. The first point, let's call this x0 or x0. And the second one is x1, x2, all the way to xn, which is the last one, right? So I'm subdividing into, if I'm dividing into 4 parts, then it's x0, x1, x0, x1, x2, x3, x4, it'd be the last point, right? So however many points, however many subdivisions you want, that's going to be my n. So I start from x0 and then that'll be xn. If I kind of go back here, kind of review here, like I wrote 1/4 as the base or the length of the rectangle. It's like, how did I get that? Well, it was 1, is that from 0 to 1, the length is 1. We wanted 4 subdivisions, so I divided into 4, right? So the reason I have 1/4 is because the entire thing had the length 1, and I divide by 4. That's why it was 1/4. So I'll kind of use that concept here. Here, the length of the entire thing is not 1. It's just between a and b. So that length is going to be just b minus a. So, and I'll just divide it into not 4 this time by n. So it's going to be b minus a over n. Right? So the reason we have 1/4 is because before it was a 1 minus 0 over 4. Right? But it could be any numbers. Okay, so this number, this little letter that looks like a triangle, this is, I'm going to read this as a delta x. So delta usually in math represents like a change in value. So from like a first chunk to the second chunk, right? So this is just a notation that we're going to be using. So approximated area. So I can kind of run the same argument. So like the first rectangle, if I were to use right, so this is x1, this is x2. If I were to use the right endpoint, the length of the rectangle is 1 over delta x, which is b minus a over n. How about the height? It's just whatever the function is. So it's f of x1, right? So if f of x is x squared, then it's whatever this number squared, right? If f of x is 1 over x, then whatever this number is 1 over that. So whatever the function is, I plug it in this number, whatever answer you get, it will give you the height of the function, right? So approximate area is going to be like delta x times f of x1. That gives you the first area of the first rectangle. And the second one is delta x times f of x2. That gives you the second rectangle, area of the second rectangle. So I don't know if it's too much. So this first rectangle, this will be the second rectangle, and then keep going. Delta x f of x3 gives you the area of the third rectangle, right? And all the way to delta x f of xn, the last one is n, right? So if I have 4 subdivisions, then the last one is going to be x4, right? I have 4 numbers. Okay. Again, I can kind of do, I can factor out delta x. So I can say delta x f of x1 plus f of x2 plus dot 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 f of xn. I don't know if you guys remember the sigma notation. There's a notation for when you try to add a bunch of numbers. It's like f of x1 plus f of x2, f of xn. Is there like a better notation to represent this sum? So we can do delta x times sigma f of xi. I goes 1 to n. I know you guys are freaking out maybe. This means how many terms you're gonna, so this symbol is called sigma. Maybe we should write that down. Sigma. That's a Greek letter for letter S. That's just equivalent of S in Greek letter. So it just means sum a bunch of stuff, right? So I'm adding first thing, I'm adding the second one, adding nth one. So it says start from the first one, go all the way to n. So for previous question, it was 1 through 4, right? But if you want to have 100 subdivisions, then it will be 1 to 100. That means like I have 100 numbers to add up. How do I find each number? Basically, this is like a counter. So when x is 1, that's like when I is equal to 1, this is like a counting. It's like this is like the first one. x of the first. And then when n is 2, then it's x f of x2, right? So this is just shorthand notation to write that. Now, how do I find the exact? So like here, it is approximate area, so A is approximately equal to. Is there an exact way to find exact answer? The answer is kind of yes. If you let n to go infinity, so if you have like a billion subdivisions, if you have a billions of these, then your area is going to get as accurate as you want. So if you can take the concept of a limit, so you can kind of do this. I can say limit as n goes to infinity, delta x, sigma f of xi as I goes to 1 to n, where delta x is just b minus a over n. We talked about that before. So this will be a symbolic way of getting exact answer. The first one is, oh, like I go from 1 to 100, so that's still approximation. But what if it's theoretically you can let n to be infinity? Then this will give you theoretical, but exactly the answer you're looking for in terms of the area. Since we talked about sigma notation here, I'm going to spend some time kind of going over the sigma notation here. So we want to see, let's look at the first one. I'm adding 1 through 100. So when you add a bunch of numbers, sometimes you can find a pattern, and then we can simplify the answer a little bit. So this one we can do like, oh, isn't it just, one trick is I can add like something like this. I can add all the way to 1, right? So I want to find what number I get from if I add 1 through 100. So what I'm going to do is I'll just add another 1 through 100 again, but like in backward, right? So that means I'm going to get 101 plus 101 plus 101 plus all the way to 101. Well, I know it's going to be 100 times because there are 100 numbers. So that'll be 101 times 100, which is 10100. That's if I'm adding 1 through 100 twice, right? So I can subtract, I can divide that by 2. So I get 5050. So if you add 1 through 100, the answer you get is 5050. So that's the little shortcut. Here, let's look at B. Looks kind of complicated. I see this notation again. The sigma notation means you're adding a bunch of stuff. This is like a counter. It tells you how many numbers you're going to be adding. So just by looking at, oh, it's 1 through 5. So that means in my head, I'm like, oh, so 1, 2, 3, 4, 5. So this is when I is equal to 1, I is 2, I is 3, I is 4, I is equal to 5. They're saying to add 5 numbers. So what 5 numbers am I adding? So by looking at the numbers on the top and bottom, I know there are going to be 5 numbers. It says add 5 numbers. And this tells you what 5 numbers to add. So it says I squared. Okay, so when I is 1, you square that number. So that's 1 squared. Then when I is equal to 2, square 2, that's 4. When I is equal to 3, again, this tells you what number to add. So 3 squared, so that's 9, and then 16 and 25. So whatever that is. Be 55. All right, let's look at part C. Property, this is what we're going to be using. Let's look at this. I noticed it's just 1 a number. There's no I in it. I'm going from n to 1 to n. Here, like imagine, let's do easier one first and see if we can find the pattern. Let's say I have something like this. So instead of n, it's a little scary. What if I have 1 through 5? 1. So that means I'm just adding 5 numbers. 3, 4, 5. Because I'm looking at the counter, it tells me how many numbers to add. And this tells you which numbers to add. Well, it just says 1, so it doesn't matter what I is. So when I don't see I here, that means no matter what I it is, you're just going to add that number, which is 1. So 1, 1, 1, 1, 1. Isn't it just 5? Yeah. So this is just complicated way of saying add 1 5 times, basically. Well, don't I just get 5? Yes. So here, so if I go from 1 to 10, sigma 1 to 10, 1, that'll be just 10, right? So if I go 1 to n, 1, it will be just n. All right. So that's kind of weird, but it's just a complicated way of saying add 1 this many times. Let's look at part 2. Okay, so the sigma and then 9, well, I see C instead of 1. I think it's going to be kind of similar. So again, I'm going to look at like an easier case. I goes from 1 to 5, C. So again, like I know it's going to be 5 numbers added, right? And again, I don't see I in it, so every time it's going to be C. So C, 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 C. Well, C plus C is 2C. 2C plus C is 3C, and so on and so forth. So shouldn't it just be 5C? Right. So if I did from 1 to 10, that'll be, I'm adding 10 C's, so that'll be 10C. So I'm going 1 through N. Each time I'm adding C, so that'll be just N times C. Okay. All right, let's look at part C here. I mean, part C is right here. This one is, again, this is kind of like, this is I, so I'm adding 1, and the next one is going to be 2. So let's say, for example, if I go I goes from 1 to 5, I. So 1, 2, 3, 4, 5. So I'm adding 5 numbers. This tells you what numbers to add. So when I is 1, this is 1. When I is 2, this is 2. Because now they're saying to add I. So this is when I is 1, I is 2, I is 3, I is 4, I is 5. So I is like a counter. They're saying whatever I is what you're adding. Because that's what it says here. It says I. Okay. So if I have I goes from 1 to 10, I means 1 through 10. I goes 1 through 100, that means 1 through 100. That's what you're adding. And this one you have to remember, the formula is n plus 1 over 2. So for example, if I'm adding 1 through 1,000, this means 1 plus 2 plus all the way to 1,000. What do I get? According to our formula, is 1,000 times 1,001 over 2. So it's kind of like what we did in the very beginning. We're just adding same thing again twice and then dividing that by 2. All right, so that's that. Let's look at this one. This one, I'm adding x squares. So this is kind of like if I do 1 through 5, I square. This means 1 plus 1 square plus 2 square plus 3 square plus 4 square plus 5 square. Okay, this is complicated. The formula you kind of want to remember is n plus 1 to n plus 1 over 6. And then last one is cubic 1. Where is it? Right here. So cubic 1 is more complicated. It's actually n plus 1 over 2. So it's like, oh, isn't it the same as this? Yeah, but there's extra square. All right, let's look at the next example. Express the following in closed form. So I have more complicated situation here. But remember, this is just a sum. So basically, we can regroup things in different ways. So here, what I can do is I can regroup them like this way. 2i over n, I goes from 1 to n, plus I goes 1 to n, 1 over n. So I split this into 2i over n and 1 over n, right? And then I'm just, these are all added, so I can just pretty much add however way I want. According to this, like I changes, but 2 and n are just fixed number. So basically we can factor that out also. So here I can go 2 over n, sigma I goes 1 to n I, plus here again there's no I in it, so we know what that is. If you look at what if I'm adding bunch of constants here, just n times c. So in this case, for example, 3, c is just 1 over n. So here this is going to be, let's make it a little bit bigger. It's going to be n times 1 over n, right? Well, we know what this is, right? That's n plus 1 over 2. So that's going to be 2 over n plus 1 over 2 plus 1. So this comes from the formula right here, right? And this is here, right? Right, so whatever that is, I can cancel out 2, and then it'll be, I can cancel out n, so it'd be n plus 1, so n plus 2. let's look at the next one. Looks more complicated. There's a limit and all that stuff. So let's kind of forget the limit for now. Let's take the limit. So let's ignore limit for now. So just look at this. 1 plus 2i over n squared, 2 over n. Again, let's see which one has n. So this one doesn't have n in it, so that's just constant. So I can, again, because we're adding a bunch of stuff and we have constant in every term, basically I can factor that out. So I'll factor that out like this. There's a 1 to n. 1 plus 2i over n squared. I'm going to factor that out. 1 plus 2i over n squared is 1 squared plus 2 times 2i over n plus 4i squared over n. Right? I'm using the fact a plus b squared is a squared plus 2ab plus b squared. So I can do here 2 over n sigma 1 to n, 1 plus 4i over n plus 4i squared over n squared. It should be n squared. Right here. Again, I'm adding these three terms. Everything is added, so I can kind of separate those additions. 2 over n. So I go sum I goes to 1 to n 1 plus sum 4i over n I goes to the n 1 to n plus y goes to 1 to n 4i squared over n squared. There's a lot going on here. Again, I'm looking at the first one. This one is just n. 4 over n is the constant. I is the one that changes, so I can factor this one out. Same here, 4 over n squared is constant, so I can factor it out. So 2 over n. First one is n plus, let's factor out 4 over n sigma 1 to n I plus factor out 4 over n squared sigma I squared. And so then I can use the formula n plus 4 over n. Again, this thing becomes n plus 1 over 2 plus 4 over n squared. The next one thing becomes n plus 1, 2n plus 1 over 6. Yikes, that's a lot. Okay, we still have some more to go. This one gets distributed here, distributed here, distributed here. So that will be 2 over n times n. So that'll cancel out, plus 2 over n, 4n plus 1 over plus 2 over n times n plus 1, 2n plus 1 over 6, and then there's 4n squared, right? So now I'm taking, so the first one is just 2. Now I'm taking n to infinity, so take now n goes to infinity. So the first one is just 2, so that's there, plus second one, if you look at the power of n on the top, that's going to be n squared when you factor this out. I mean, when you multiply this out. On the bottom is n squared, so basically they have the same power, so n goes to infinity. So that means it'll just go to coefficient. So that's 8 over 2 plus, and the third one, on top there's n and 2n. So it's going to be n cubed. Bottom also n cubed. Power is the same. That means it just goes to coefficient. 2 times 4 times 2 on top, and then bottom is going to be just 6. So that'll be 16. Oops, that's going to be 16 over 6. That's 2 plus 4 plus 8 over 3 if you simplify. So that's 8 plus 8 over 3. So that's 2. That's 10 over 2 over 3. Like that. All right, that was a lot of work. So basically, this is the formula we kind of talked about. Sigma 1 goes to n f of x I. They use now I little star. So usually, before we use the right endpoint, but basically they say you can put any point you want, basically. So kind of this is still the same. If Rn, then it's the right end point, right? So that's what it says. Now I'm gonna have you do example 5. My hint is start with n subdivision. Use Rn, right end point. It just makes it easier with the calculation. And then take n goes to infinity, and then you'll get the exact answer. And the way you start will be, your setup is going to look like this: to n f of 2 over n I times 2 over n. So this is delta x. Then you can go from there, and then you take the limit as n goes to infinity, and then whatever answer you get, it will be your answer. And your final answer should be 14 over 3. And the next question is, so I'm going to have you pause and actually do it, and then see if you get 14 over 3. And example 6 is determine the region whose area is equal to. So you don't have to actually calculate it out, but like what area does it correspond to? So first I'm noticing is 4 over n, so the area is going to be somewhere over like length 4. I look at the first one, like, okay, it's a 3 plus something, so I'm like, okay, you're starting from 3. So 3 to 7. The reason I chose 3 to 7 is because it's 3 and then you kept adding something. So, okay, when I 0, you're looking at 3. So you're starting from here, right? And then 4 over n is my delta x. That means this length is 4. That's why I put 7. And basically the function is fifth function, right? So its area under f of x is x to the 5th over interval 3 to 7. All right, this is it. This is long section, but we're pretty much done.